Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up our summary of numerical series. In the first couple of videos, we sort of went back over what it meant to be absolutely convergent, conditionally convergent, and divergent for series. We also saw the sort of differences between what it means to converge as a sequence as opposed to converging as a series. Then in the sort of second part of this summary, we spent some time talking about the sort of different speeds of functions, different speeds of expressions, from logarithmic to power to exponential to factorial and beyond. And we saw how those speeds sort of directly relate to the convergence or divergence of series. In this video, we're going to finish this summary by sort of going back over all the different tests that we've developed so far from sections 11.2 through 11.6, and then taking a look at some examples where we're going to be spending some time not only working through the examples, but talking about how we would choose an appropriate test. So in other words, this is going to be sort of summarizing the strategies for choosing the appropriate test for convergence and divergence of infinite series. So, to start off with, let's go ahead and just summarize everything we've discussed thus far for testing numerical series. So, to start off with, we, at the sort of beginning of our discussion back in 11.2 and 11.3, we introduced two very special types of series. These are not tests, but these are types of series that we understand the behavior of. We had geometric series, which are the sum of r to the n, where r is a constant value. So these are sums where you have a constant base and the exponential is based, or the exponent is based on your actual index for your series. And we know exactly when these are convergent or divergent. We know these are absolutely convergent when that base or that common ratio in absolute value is less than 1. And they are divergent when you have the absolute value of r greater than or equal to 1. So for geometric series, we understand when they converge and when they diverge. Technically, we also have one other piece of information. We don't use it too much, but geometric series we actually have the most information about because we also have a formula for how they sum up. So not only do we know when they converge, we know that if they converge, the sum from n equals 0 to infinity of r to the n is 1 over 1 minus r, provided that the absolute value of r is less than 1. Obviously, that looks a little, let's just rewrite that so that's clear. Absolute value of r less than 1. Obviously, if the absolute value of r is greater than or equal to 1, there's no summation formula because it's divergent. This is pretty rare for us. Again, remember, our focus is not on actually summing up the series, just understanding when that sum would be finite. In other words, when the series converges. But technically, we do have this formula, right, for a geometric series specifically. Another really important type of series that we've discussed is the p-series. P-series are the sum of 1 over n to the p, where p is that constant value. So now here the power, or the exponent, is a constant value. We know that these are absolutely convergent when that power is greater than 1, and divergent when that power is less than or equal to 1. Keep in mind that in both of these, I'm mentioning absolute convergence here because, well, in this one, it's automatically absolutely convergent because we have always positive terms. And in this one here, it is also absolutely convergent, even if that r in is negative, as long as its absolute value is less than 1. So these are two types of basic series that we know their behavior of based on just the sort of format of that series. Now we can begin sort of recapping all the tests that we have for series that don't necessarily just fall into these two very specific situations. Keep in mind, unless something is literally in one of these two formats, then it is not geometric or a p-series. It might be similar to a geometric or p-series, but to actually be considered one of these two types of series, you have to explicitly fit those two formats. All right, so let's go over the types of tests that we've developed so far, and we'll sort of do them in the order that we encountered them. So the tests that we've developed for series start with the test for divergence. The test for divergence says that if the limit of the sequence is not equal to 0, then the series diverges. So if the sequence converges to any value but 0, or if the sequence diverges to infinity, negative infinity, or diverges because it doesn't exist, then the series automatically diverges. Keep in mind, this is a one-directional statement, meaning that if the limit is 0, then you get no information. When should you use the test for divergence? Well, you should almost always consider this test. You should always, at least at the beginning of looking at a series, consider the test for divergence. It is very easy to perform computationally because it's literally just a limit. Oftentimes, you can at least roughly do that limit in your head. However, remember that anytime that limit comes out as 0, you get no information. So while the test for divergence is always worth thinking about at the beginning, it often yields no information. So you should always start by thinking about it, but don't expect that every series is going to be handled with that test for divergence. All right. The second test that we introduced was the integral test. The integral test came from 11.3. It said that if you can find a function, f of x, that is always positive, continuous, and strictly decreasing, so 3 conditions. Remember that the sort of hardest condition, or the one we often actually have to check, is the strictly decreasing one. And remember, this function has to be a corresponding function, meaning that f of n has to equal a sub n for all n. Then the improper integral has the same behavior as the infinite series. And what do we mean by same behavior? Well, it means that if the improper integral converges, so does the infinite series. If the improper integral diverges, then so does the infinite series. The integral test was very important theoretically because we use the integral test to actually develop our knowledge of the p-series. Couple little notes about the integral test. Keep in mind, since f of x must be always positive, this test only works for series with always positive terms. So if you encounter something that has some positive and some negative terms, or like an alternating series or something like that, integral test cannot be used because it must be always positive. Also keep in mind that while the integral test tells us that the improper integral and the series will behave the same, if they converge, meaning that they actually converge to a finite value, the values will actually be different. We actually showed in the proof of the integral test that the infinite series is going to sum up to something that is larger than the value of the improper integral. So remember, this test is again about the behavior, not the actual value. Finally, in terms of when should you use the integral test? Well, unfortunately, this should be really a test of last resort. The reason that integral tests should sort of be used as a very last resort is that integration is tricky. There's a lot of expressions out there that are very challenging to integrate. So you should really only use the integral test if the other tests fail and you can actually see a clear way of integrating the corresponding function. If you're looking at something as a series and you're thinking about the corresponding function and you have no idea how you would integrate that function, then it's not worth doing the integral test because you're just going to get stuck on the integration. So you got to make sure to probably try some of the other tests first, and then also make sure that you actually see a way of integrating the corresponding function. As just a side note, oftentimes, if you've looked back over some of the examples we've done, we often use integral tests when we have logarithmic expressions in the test. And that just happens because those logarithmic expressions, when we talked about them in the sort of previous part of the summary, they're one of the slowest growing expressions out there. But unfortunately, because they do grow to infinity, they sort of ruin some of the direct comparison and limit comparison tests. So sometimes you need to use integral tests to deal with them. So sometimes if you see a logarithm in your series, you might consider the integral test, but generally it should be avoided because it is one of the harder ones to do computationally. All right, let's continue from there. We had some comparison tests. So these came from 11.4. We had the direct comparison test, which said that if we have two series, some a sub n and some b sub n, both with always positive terms, and we're going to assume that the terms of a sub n are bigger than the terms of b sub n. So this series here has strictly larger terms than the other. Well, then we said that if the sum a sub n converges, then the sum b sub n will also converge. So if the series with the larger terms converges, then the series with the smaller terms will also converge. Sort of the idea there was that if the larger one is finite, then the smaller one must be finite. And if the smaller one diverges, so the series with smaller terms diverges, then the larger one will also diverge. So if some b sub n diverges, then some a sub n will also diverge. Remember again that this is another test that is restricted to series with always positive terms. That's part of the assumption here, that they have always positive terms. And remember that this is a comparison test, meaning that when you do this, you need to compare it against a series you know the behavior of. For us, the two types of series we know the behavior of are geometric or p-series. So if you're planning on using direct comparison, you need to be able to compare your series against a geometric or p-series. Direct comparison test, again, very useful to prove theoretical results, but it's not particularly useful when actually just trying to handle something computationally because of the fact that you actually have to show that direct inequality there. A lot of times this is used when your expression involves a bounded function. That is one of the times that it is very useful. So if you see things like sine or cos or arctangent, any of those bounded functions, you can use direct comparison test to basically say that those bounded functions act just like finite values. You can use it in other situations, but to be honest, limit comparison test, which we're going to talk about next, is often much easier. So again, direct comparison test, there are some very particular situations where it can be useful, but often the limit comparison test is a bit easier. All right, so let's talk about that limit comparison test. So limit comparison test says you have two series, some a sub n and some b sub n. Again, both with always positive terms. And what you do in limit comparison test is you take the limit of the ratio of the terms. So a sub n divided by b sub n. And you calculate the limit of that. For the limit comparison test to work, you need that limit to come out as a finite number and also non-zero. Doesn't matter what the value is, doesn't matter if it's 1/3, 7, a million, whatever, as long as it's finite and non-zero. So we don't want this limit to come out as 0, and we don't want it to come out as an infinity. Then, if that is true, then these two series have the same behavior, meaning that they either both converge or they either both diverge. Once again, this is restricted to series with always positive terms. Also, keep in mind, this is another comparison test, so you would only use this when you're going to compare against a series you know the behavior of, so either something geometric or p-series. This limit comparison test is one of the most useful computationally, meaning that for just handling a random series that we're given as like an exercise or a problem or a quiz or an exam, LCT is one of the most commonly used one. It's super useful when you want to remove lower order terms. We've done lots of examples of that where we have these polynomial expressions and we just get rid of all the lower exponent terms because we know that they're not going to matter in the long run. That's what limit comparison test really does. It often is also very useful when you have an expression that involves a composition. You see something like sine of 1 over n. We've done examples where it turns out as a series, sine of 1 over n acts just like 1 over n. And we do that through that limit comparison test. So this is a really, really important one computationally because that limit is easy to do. And then we get that this result tells us that they either both converge or they both diverge. The big advantage of this limit comparison test is you do not have to show this strict inequality that one is always greater than or equal to the other. Well, instead, you just need to calculate that limit and make sure it's finite and non-zero. So this one here, very, very useful. All right. Now we're ready to talk about one finally that applies to things that are not strictly positive terms. Right? All the other ones that we've talked about so far, integral test, direct comparison test, limit comparison test, all of those required that you have always positive terms. So we now need something that can handle ones where we have sometimes positive, sometimes negative terms. And that's, of course, an alternating series. So we have the alternating series test. So suppose you have an alternating series. Remember, the definition of an alternating series is you have that alternating component minus 1 to the n, and then you have that a sub n, the magnitudes, where the a sub n's are always positive. And remember that those a sub n's need to be always positive, so this thing really alternates, right? So it goes positive, negative, positive, negative. So the alternating series test says that if you can show that the limit is 0, so the limit of those magnitudes goes to 0, and those magnitudes are strictly decreasing, then you automatically know that the series converges. So, a couple notes on this guy. Obviously, this test only applies to alternating series. That should sort of go with the name, but it's important to remember that. You're not going to use the alternating series test on something that has strictly positive terms. It has to be alternating to use this. Second note, which is just really about sort of the terminology and the sort of conceptual stuff behind the scenes. If that limit, when you're checking that first condition of the alternating series test, is not 0, then the series will diverge. But it doesn't diverge by the alternating series test. The alternating series test is something that either says the series converges or gives you no information. So if that first condition is not satisfied, if that limit is not equal to 0, we know the series will diverge, but it'll diverge by the test for divergence. So just be very careful there, right? A lot of times it's tempting when that first condition fails to say something along the lines of my series diverges by the alternating series test. That is always incorrect. If that first condition is not met, then your series will diverge, but by the test for divergence. In terms of strategizing this, well, obviously it's easy to identify when you're supposed to use this. You have to have an alternating series. One important thing to remember, though, is that anytime we encounter an alternating series, we always begin by testing for absolute convergence. We always take the absolute value of the terms and analyze that first. Because remember, if it converges in absolute value, then it's absolutely convergent. Only if it diverges in absolute value, then do we need to use the AST to investigate conditional convergence. So the main thing here to remember is that when you see an alternating series test, so alternating series like this, you know that the alternating series test is a potential, but you should really only do it second after testing for absolute convergence. We always look for absolute convergence first. All right, let's get to the last two tests that we talked about when we talked about these most recently in 11.6, which are ratio and root test. Ratio test says that you consider the limit as n goes to infinity of the absolute value of an plus 1 over an, and you let that be equal to the limit L. If that L is less than 1, then you know that your series is absolutely convergent. If L is greater than 1, then you know your series is divergent. And if L is equal to 1, then the ratio test yields no information. Remember that the ratio test is sort of special along with the root test, because when it says that something converges, it doesn't just say that it converges, it actually tells you that the convergence is absolute convergence. Remember, in terms of strategizing ratio test should always be used if your expression involves a factorial. So anytime you see a factorial or a modified factorial or anything like that, you automatically know ratio test. Ratio test can also be used as long as at least one of the terms is exponential order or higher. So exponential, factorial, n to the n, anything like that. You can use ratio test. Doesn't necessarily mean it's the best one to use, but you can use it. This does mean, though, that if everything is polynomial order, so if that means your expression has just things like n cubed and n to the fifth and n and constants and things like that, ratio test is not going to yield any information, so you should avoid ratio test. Ratio test really needs exponential order or higher things in there to yield information. Keep in mind also, in the situation where L is greater than 1 and you get that the series diverges, actually test for divergence will also give you that information, though sometimes ratio test, especially when there's like factorials present, is still easier to do than the test for divergence. Root test, very similar to ratio test, except that here we investigate the limit as n goes to infinity of the terms in absolute value to the 1 over n. And of course, that's the root. It's the nth root. And we set that equal to L. Same sort of information here. If that L is less than 1, then we get that the series is absolutely convergent. If the L is greater than 1, then we get the series is divergent. And if L is equal to 1, then unfortunately the root test yields no information. Remember, similar to the ratio test, the root test, when it detects convergence, guarantees that the convergence is absolute. Keep in mind, we also talked about how the root test is stronger than the ratio test. Meaning if you get L equals 1 with the root test, you get no information, and you also know that the ratio test will yield no information. So if the root test doesn't work for you, well, then you can just skip the ratio test because it's also not going to work. The root test should always be used if your expression has a single term raised to a function of n power. So if you ever have something where you have an entire term and it's raised to like the nth power, so one big thing all raised to like the nth power or the 3n power or the n squared power or anything like that, you should use root test. Root test can also be used as long as there's at least one term of exponential order or higher. So something that's exponential, factorial, n to the n, any of those types of things, then you can also use root test. Once again, though, if everything is polynomial order, so if you just see like n cubed and n squared and n all throughout your expression, then the root test should not be used because it's going to yield no information. It can't detect anything. So there we go in terms of quickly summarizing all of the tests that we've covered from 11.2 through 11.6. We've also now sort of discussed how to strategize and choose these different sort of tests. Keep in mind that testing series for convergence and divergence is very similar to integration in the sense that there's no sort of immediate way when you're just given a series to know exactly what you're supposed to do. You have to sort of play around with it. It's more of a creative process. Also, just like with integration, sometimes there are several ways to approach the same exercise, right? The same series can sometimes be tested in several different ways that all result in the same conclusion. So it doesn't mean that there's always just one right way to approach testing a series. So let's get into some examples of, again, just sort of practicing all these, but also strategizing the correct choice of test. All right, so here's our first one. For all of these, every question is going to be about whether or not the series is absolutely convergent, conditionally convergent, or divergent. Notice that this is an alternating series, so all three things are possible. How should we begin? Well, since it's an alternating series, and notice that everything is polynomial in order, meaning that we don't want to avoid ratio and root test because we just have n to different powers in here. What we should do is we should put it in absolute value and analyze that. So we're going to start by considering the sum of the absolute value. Okay, so let's go ahead and do that. That means we're actually going to be looking at the sum 5n squared plus 6 over square root n to the 8th plus 1. And of course, we're still running from n equals 2 to infinity. You could, of course, just omit that n equals 2 because we know that starting spot has no impact on what behavior it shows. It would have an impact on what it adds up to, but not whether or not it adds up to something finite or whether or not it diverges. But, we'll just carry on the n equals 2 because that's what was given to us. So now we want to start by considering this. So how are we going to analyze this? Well, if you wanted to, you could do a test for divergence in your sort of head, but you can sort of see that down here, we have like a square root of n to the 8, which is going to be like an n to the 4th, and that n to the 4th is definitely going to outpace the n squared, so this is definitely going to go to 0. So unfortunately, test for divergence isn't going to give us any information. What would be nice, though, is if we could just sort of lop off that 6 and that 1 and study it from there. So that sort of sounds like an LCT. Remember, LCT is very good at chopping off additions and subtractions, those unnecessary terms. So we're going to try to LCT this with the sum. And now I will sort of just omit and just sort of write out the expression. It seems like up top, probably what matters is the n squared. And in the bottom, it probably is just the square root of n to the 8th. Now, of course, that's equivalent to the sum n squared over n to the 4th, and that, of course, is just the sum of 1 over n squared. And notice that that is something we know a lot about, right? This thing here, well, this converges as a p-series, right? Because we have p equals 2, which is greater than 1. So if we can actually use the LCT, then we can say that this series will converge because it should act the same as this. So let's actually go ahead and try that LCT. So to do the LCT here, we need to do the limit as n goes to infinity. We take the terms of our series, so 5n squared plus 6 over the square root of n to the 8th plus 1, and then the terms of the comparison series, so 1 over n squared. Okay, we can go ahead and flip this up there, and we can get the limit as n goes to infinity, 5n to the 4th plus 6 over square root n to the 8th plus 1. Okay, now, since everything's just n to different powers, we can take the largest power in the denominator and multiply top and bottom by 1 over that. We got to be a little careful, though, here. If we do that, then we'd need to do that in square root. So we'd want to multiply by something that's 1 over the square root of n to the 8th. So that would be n to the 4th. So 1 over n to the 4th, 1 over n to the 4th. But again, our plan is to treat this as the square root of 1 over n to the 8th, so that we can actually mix it with that radical there. All right, if we do that, then we would have the limit as n goes to infinity. Up top, we get 5 plus 6 over n to the 4th. Down in the denominator, we'd have the square root, 1 plus 1 over n to the 8th. So there we go. Now, we know that these terms go to 0, so this thing looks like it's going to come out as 5 over root 1, which is 5. Important thing to remember is that a lot of these tests have different sort of things. What are we looking for? Do we want it greater than 1, less than 1, equal to 0? Right? All the tests are different. Here, the important thing is that we want it to be finite and non-zero, which it is. So that means that our LCT was successful. So we now know that this acts just like this. So we can now say that the sum of 5n squared plus 6 over the square root n to the 8th plus 1 converges by LCT, since sum 1 over n squared converges. Okay, so we now know that this converges. Now, was this actually our series? Well, we can look back. Our series had that minus 1 to the n in it, so we put it in absolute value, and we showed that it converges. That means our series, sum minus 1 to the n, 5n squared plus 6 over the square root n to the 8th plus 1, is absolutely convergent, because when we put it in absolute value, it's still converged. It's very important to get this last statement down there, because if you just ended here, well, then it doesn't really answer the question that was being asked, which was about the behavior of this series. But we showed that this right here in absolute value is equivalent to this. This converges, so our series is absolutely convergent. Make sure you always sort of end with a statement about the series that was actually being asked about. So this guy was absolutely convergent. All right, this is sort of a classic example of LCT, because basically the LCT, one of its most common uses is to say that that like plus 6 and that plus 1, those sort of unnecessary extra terms can be dropped. That's what the LCT really is good for. Okay, let's take a look at another one. All right, so we want to determine if this series is absolutely convergent, conditionally convergent, or divergent. We have the sum of 8 times n factorial over 1 times 6 times 11 times 5n plus 1. And remember, this denominator is what we call a modified factorial. It's a factorial-like expression, but instead of going 1 by 1, it looks like it's skipping by 5s here. You're taking 1, then times 6, then times 11, all the way up to 5n plus 1. So we don't even need to think about where we should start here. As soon as we see the factorials, we don't worry about anything else. We just know to go straight to ratio test. So we don't even need to worry about anything else. Factorials are one of those things that as soon as we see them, we know that we should use ratio test. Notice that both this and this are factorials. If just one of them was there, if it just had n factorial there, or if it just had this in the denominator, we would still use ratio test, because as soon as we see one instance of a factorial, we know to use ratio test. So let's go ahead and do our limit as n goes to infinity. Absolute value an plus 1 over an. That means we're going to have the limit as n goes to infinity. An plus 1 is going to be 8, then times n plus 1 factorial, divided by, and then 1 times 6 times 11 times times 5n plus 1, because remember it's a factorial, so it always has everything that was previously there, and then times 5 times n plus 1 plus 1. So it has that everything that was there for the nth term, and then it has the n plus 1 part. Then in the denominator, the a sub n, well, that would be 8, and then times n factorial, and then divided by 1 times 6 times 11 times times 5n plus 1. Okay. Notice that this one has always positive terms, so those absolute value bars can just be dropped. Also keep in mind that that means that in terms of the options here, since it has always positive terms, conditional convergence is out. So let's go ahead and drop those absolute value bars and also simplify. To simplify, we're going to swing this up top. So it looks like we should have 8 and times n plus 1 factorial, and then 1 times 6 times 11 times times 5n plus 1, all divided by, in the denominator, looks like we have 8, n factorial, and then down here, we have this whole mess there. So 1 times 6 times 11 times times 5n plus 1 times 5 times n plus 1 plus 1. Okay, Now, we have a lot of cancellations to do. First of all, notice that these parentheses are here to tell you that this 8 is not being multiplied onto that n plus 1. It's being multiplied onto the result here. So since we have an 8 on both, we can just cancel those out. Same thing here. We can cancel all of these things down to just having this left. So let's go ahead and do that. We now have the limit as n goes to infinity. Up top, we have n plus 1 factorial. And in the bottom, we have n factorial. And we only have this last one that remains. That's 5n plus 5 plus 1. So that would be 5n plus 6. Okay. Now we can go ahead and simplify here. Remember, there's this sort of trick that n plus 1 factorial can be thought about as n plus 1 times n factorial, because what is a factorial? It's n plus 1 times n minus 1 times n minus 2 times dot dot dot. So that means n plus 1 factorial is n plus 1 times n minus 1 times dot dot dot. All of that is n factorial, so we get that right there. That means we can cancel that factorial with that and just be left with an n plus 1 up top. So we now have the limit as n goes to infinity, n plus 1 over 5n plus 6. So there we go. Now we have this limit. This is very easy to figure out here. We can just go ahead and multiply 1 over n, and we should see that we have the limit as n goes to infinity, 1 plus 1 over n, 5 plus 6 over n, and of course that is going to be 1/5. What do we care about here? Well, we're doing ratio tests. Remember, for ratio and root, we compare the limit against 1. In this case, we get less than 1. So this tells us our series is absolutely convergent by ratio test. So there we go. This guy, there wasn't much to strategize at the beginning because we had those factorials. As soon as we saw those factorial expressions, we knew to go ahead and use ratio test. We went ahead and did the ratio test, had to be a little careful with that modified factorial there. But remember, every factorial always has all of the previous terms. That's why when we write this out, I wrote everything from 1 times 6 to n times 11 up to 5n plus 1. And then the next one, 5 times n plus 1 plus 1. Okay, so that was an example of strategizing the ratio test and then seeing that that ratio test led us to deduce that it was absolutely convergent. Okay, let's try another. All right, here we've got an alternating series, minus 1 to the n, 5 to the n over n to the 5th. Right? Now, since it's alternating, all the possibilities are there. Absolutely convergent, conditionally convergent, divergent. So we've got options of how we want to approach this. If you wanted to, this is actually a question where there are a bunch of different ways to approach it. You're probably not going to want to use a comparison test because if we look at this thing, we've got two very different types of expressions. So you've got that 5 to the n, which is exponential, and you've got n to the 5th, which is polynomial. Comparison tests are very good when everything's the same type, meaning all polynomials are all exponentials. Since we have an exponential term, that does mean that ratio and root test are possibilities. That doesn't necessarily mean they're the best ones, but they are certainly possibilities here because we have something that is at least exponential order. So if we want, we can go ahead and try ratio or root test. Now, if you use ratio or root test, you don't need to worry about putting things in absolute value because the test does that yourself. So if we want to, right, method 1 is, well, since we just did ratio test, let's try root test. Let's use root test. So to use root test, we would take the limit as n goes to infinity. We take the absolute value of a sub n to the 1 over n. In this case, we get the limit as n goes to infinity, absolute value minus 1 to the n, 5 to the n, n to the 5th, all to the 1 over n. Now, here, that absolute value is going to matter. It's going to remove that alternating piece. Otherwise, this is always positive, so we don't need absolute value bars for that. And we get the limit as n goes to infinity, 5 to the n to the 5th, to the 1 over n. Now, we can distribute that 1 over n to both things. Notice that if there were any pluses or minuses in the expression, we wouldn't want to use root test because it's impossible to distribute exponents over addition and subtraction. But here, since we just have a quotient, it's very easy to distribute this. So you want to sort of think ahead about whether or not it's going to be doable. So in this case, it's nice and easy here. Power to a power multiplied. So up top, we're going to get 5. And in the denominator, we're going to get n to the 5 over n. Now, keep in mind, this is an indeterminate form. This is infinity to the 0. But we have a trick for dealing with this. We stated a very important limit for a root test is that the limit as n goes to infinity of n to the 1 over n is 1. That's very, very useful. So let's go ahead and rewrite this as limit n goes to infinity, 5 over n to the 1 over n to the 5th. Now we can use this to say that that's going to be equal to 1. So this is 5 over 1 to the 5th. And of course, 1 to any exponent is just 1. So 5 over 1, that's 5. So since we're using root test, we then need to compare that against whether or not that's larger than or less than 1. In this case, it is greater than 1. So by root test, our series diverges. So there we go. We know that this is a divergent series. Now, I said method 1 here because on your own, what you can try is method 2. You can use ratio test. It will also work. It'll be a little bit messier, but it will work. And the reason it'll work is, again, there's something of exponential order. Also keep in mind that when root test or ratio test says that something diverges, that means it also diverges by test for divergence. So you could also try method 3 and try test for divergence. Now, test for divergence, something that's sort of interesting here is that you have to analyze this limit. And that limit is going to be an infinity over infinity. And unfortunately, it's going to take like 5 iterations of L'Hopital's rule to remove that n to the 5th and actually get that this thing diverges. So while test for divergence will work, it's probably better to use a root or ratio test in this situation. But if you want, you can go through on your own and confirm that both ratio test and test for divergence also work to solve this. Okay, let's go ahead and talk about another one then. So for this one, we want to determine if this series is absolutely convergent, conditionally convergent, or divergent. ln of n over n. Well, immediately notice that in terms of the options here, this cannot be conditionally convergent because this has always positive terms. We said that sometimes when we see an ln of n, that's an indicator for like an integral test. If we think about it, I haven't checked the conditions yet, but if we think about, is this integrable, right? Would I know how to do that? Well, notice I could try to do like a u sub, u equals ln x, and then du would be that 1 over x dx. So that sounds like an integral that seems doable. So maybe we can try integral test. So we're going to try to do our integral test here. Now, unfortunately, we don't get to jump right in. We have to define what the function is going to be and check the conditions. So we're going to say f of x is going to be ln x over x on the interval 3 to infinity. Okay, we've got some conditions. Continuous. Definitely, right? There's issues of continuity near 0, but we're on 3 to infinity, so we're all good. Positive. Definitely, right? X is certainly positive because it's between 3 and infinity. And ln is certainly positive because it's x is greater than 1. And decreasing, well, unfortunately, both of these are getting larger, so we need to use the derivative to really claim that the denominator is growing faster. Now, of course, for our discussion in the previous video about speeds of functions, we should be pretty confident that this grows faster than this because this is polynomial and this is logarithmic, but the derivative confirms that for us. So f prime here would be 1 over x times x minus ln x times 1 over x squared. That's quotient rule, and that looks like we get 1 minus ln x over x squared. This is always positive, and since we are past e, since we're on 3 to infinity, ln x is going to be bigger than 1. So this is negative, this is positive. Negative divided by positive is going to be negative, less than 0. Check. Okay, so all the conditions are met. So now we can consider the integral from 3 to infinity ln x over x dx. Immediately change that into a limit. So limit as t goes to infinity, 3 to t, ln x over x dx. We can do a u sub. U equals ln x. du is 1 over x dx. The original x bounds were t and 3. The new u bounds should be ln of t and ln of 3. So we can pop that stuff in there. Ln of 3 up to ln of t. Once we replace this, this is going to just be u, and all this is going to become du. So we get u du. We integrate that. We get the limit as t goes to infinity, 1/2 u squared, evaluated from ln of 3 up to ln of t. Then we pop that stuff in there. Limit t goes to infinity, 1/2 ln of t squared minus 1/2 ln of 3 squared. We don't really care about this because this is just a number. This is going to dictate the behavior. As t goes to infinity, this is going to approach positive infinity. Squaring it is just going to make it go there even faster. So this heads towards positive infinity. So by integral test, our series diverges. So the improper integral diverges. So by integral test, since we checked all the conditions, our series diverges. So this series back up here is a divergent one. Now, this integral test here, we sort of relied on saying, oh, well, I noticed that ln, and we took a quick glance ahead that this integral would be reasonable, so we went ahead and did it. This turns out to, this is definitely method 1 here. It turns out that there is a much, much faster method if you sort of recognize it. Method 2 is a direct comparison. Why a direct comparison test? Well, keep in mind that sum 1 over n diverges as a p-series. Right? If we just had 1 over n, it would diverge. But remember, we had ln of n over n, which means that our numerator was just getting larger and larger. So it wasn't just 1, it was getting larger and larger. So clearly, ln of n over n is bigger than 1 over n. So by direct comparison test, sum ln of n over n also diverges. So notice, obviously, same conclusion, doesn't matter which test you use, both conclusions would work there. Now, these are really the only two ways to approach this. And if you want to convince yourself, you can try a limit comparison test and try to say that ln of n is similar to 1 over n, and limit comparison test actually won't work because limit comparison test is basically saying that one series is sort of like a multiple of the other. But that's not true here. ln of n, it gets larger and larger. So our series is actually drastically larger than 1 over n, which is why direct comparison test actually works well here because this is just much larger than 1 over n. So you can do this either through the integral test, which is a much longer approach, but does sort of realize, that ln, oftentimes that's an integral test, so we use that. That's sort of easier strategy, harder work. Or you can be sort of clever on this one, recognize the direct comparison test, much easier, but maybe harder to recognize. Okay, let's try another one. So we want to determine if this series is absolutely convergent, conditionally convergent, or divergent. All right, first thing we should sort of think about here is what are the options? Well, it is a alternating, so all these are possibilities. We can see that this thing is going to be like logarithmic in nature. So things like ratio and root test should be out. We can consider maybe it's got a logarithm in it, so maybe we want to try to do integral tests, though I'd be a little hesitant because we'd have to deal with like integrating ln 1 over x squared dx, and that looks a little bit harder because it doesn't look like an easy u sub. Before we get too far, right, especially if you can't see an immediate thing, you should always just consider the test for divergence. So let's just consider that real quick. For the test for divergence, you really can just look at the magnitudes. You don't need to worry about that minus 1 to the n, because remember, if this goes to 0, then the minus 1 to the n times 0 is also going to go to 0. If this doesn't go to 0, well, then the minus 1 to the n is also going to diverge. So we can go ahead and just sort of look at the absolute value here. And what happens in this? Well, as n goes to infinity, that 1 over n squared approaches 0. So technically, this is approaching like 0 from the slightly positive, right? Because if n is going towards infinity, 1 over n squared is approaching 0 from slightly from the right. So what happens to ln? Well, remember, ln looks like this, and we're coming in like that as we approach 0. So this is going to head towards negative infinity. So this part here is headed towards negative infinity. Our thing is actually oscillating between, well, I guess negative infinity and positive infinity. Point is, though, is that's not equal to 0. So this diverges by test for divergence. The whole idea here is that notice at the beginning I sort of did a little strategizing. I said, okay, logarithm, maybe integral test, though it doesn't look great. I know it's not going to be ratio or root because, again, those don't do well with logarithmic expressions. So we were a little hesitant about where to go. If you're ever hesitant about what to do, try the test for divergence first because it's the easiest one to do. So if you're ever unsure, you should try that. In this case, it worked out perfectly, so we got that it diverges by test for divergence. Okay, let's take a look at another. So here we've got, again, same sort of setup. It's alternating, so we could have absolutely convergent, conditionally convergent, or divergent. First thing we should sort of recognize is that 1 over root n, that's something we know. That's a p-series, but it's stuck inside of that sign. So composition, probably an LCT. So composition implies LCT. Notice things like ratio and root definitely are going to be out because, again, we only have things of polynomial order, n to the 1/2 in there, so ratio and root's not going to work. So we like to use LCT because LCT is good for compositions. Unfortunately, though, LCT requires that we have always positive terms, so we need to start with considering the absolute value. So let's consider the absolute value here. All right, so that means we're going to be looking at sine 1 over root n. And our idea is that hopefully we can LCT that with 1 over root n. What do we know about 1 over root n? Well, this right here, this diverges as a p-series since p equals 1/2 is less than or equal to 1. So if the LCT works, then we know that this thing will diverge. So let's go ahead and see if we can do that. So what does a LCT actually look like here? Well, it's going to be the limit as n goes to infinity, sine 1 over root n divided by 1 over root n. So if we look at that, what's going on up here was n goes to infinity, sine of 1 over square root of infinity, that's going to be 1 over infinity, that's going to be 0. Sine of 0 is 0, so this is 0. And this is 0. So this is approaching a 0 over 0 situation. That means we could use L'Hopital, provided we do a replacement theorem. So let's do a replacement theorem. Look at this as limit as x goes to infinity, sine 1 over root x, 1 over root x. Now let's go ahead and apply L'Hopital. Limit as x goes to infinity. Derivative of here is going to be a chain rule, so we're going to get cosine 1 over root x, and then we'd have to take the derivative of the inside. You're welcome to do so, but keep in mind the inside here matches what's down here. So we can be a little lazy and just write 1 over root x prime over 1 over root x prime, whatever that derivative is. Not hard to do that. Of course, that's x to the minus 1/2, so prime would be like negative 1/2 x to the negative 3/2. But we can just skip it because these are going to cancel. So we get that this is then the limit as x goes to infinity, cosine 1 over root x. Well, as x goes to infinity, this is going to go to 0. So this is going to approach cosine of 0, which is 1. We're doing an LCT here, so getting a 1 is a finite and non-zero value. Check. So the LCT worked. So what does that tell us? Well, that means that this acts the same as this. So what we've just figured out is by LCT, sum sine 1 over root n diverges, since sum 1 over root n diverges. So we've just figured out that this thing diverges. Does that mean that our series diverges? Well, our series has that minus 1 to the n in there, so they're not quite the same. But what it does tell us is that if we put it in absolute value, if we get rid of that, it will diverge. So what we've just figured out is, so our series, sum minus 1 to the n, sine 1 over root n, is not absolutely convergent. So we've just figured out that our series is not absolutely convergent. Okay, now, what does that tell us? Well, that tells us it's not absolutely convergent, so it's either conditionally convergent or divergent. Now is the time to go ahead and use the alternating series test. So let's give ourselves another page to go on to. So, since this is not AC, we should use the AST now. So for the AST, first thing we need to do is take the limit as n goes to infinity of the magnitude sine 1 over root n. Again, we're now using the alternating part, but we focus on those magnitudes for the conditions. Here, that is going to approach sine of 0, which is 0. Check. And then condition 2, we need to say that sine 1 over root n strictly decreasing. Well, unfortunately, I mean, this part is strictly decreasing, but sine is a whole nother function. We should check the derivative here. So f of x is sine 1 over root x, which of course is sine x to the negative 1/2. That means f prime, well, I guess cosine x to the negative 1/2 times negative 1/2 x to the negative 3/2. So what happens here? Well, as x gets larger and larger, well, this is certainly going to be negative here. This is just going to get really close to 1, like we said. So this is definitely going to be less than 0 here. So this is less than 0. Check. So we now have that the two conditions are met. So what does that tell us by AST? So by AST, sum minus 1 to the n sine 1 over root n converges. AST tells us it converges. Doesn't tell us what type of convergence. But remember, we've ruled out that it's not absolutely convergent. So we know it's not absolutely convergent, but it does converge. So we can say sum minus 1 to the n sine 1 over root n is conditionally convergent. This is how we get something that's conditionally convergent. We first have to do the work to show that it's not absolutely convergent. Then we can use the AST to say that it is conditionally convergent. Notice that if back here we had done all this stuff and it had turned out to be compared to something like, say, sum 1 over n squared or 1 over n cubed, something that had converged, we would have been done when we got down to here because we would have known that it's absolutely convergent. But in the situation where it is not absolutely convergent, then you have to go ahead and use the AST here. So AST not used a lot. It's just in this one sort of specific situation where you've ruled out absolute convergence, and then you've used the AST to conclude that it's conditionally convergent. Again, also keep in mind LCT was useful to us here because we had that composition, and inside was something that we understood, which was a p-series. Okay, let's take a look at another. So here we've got minus 1 to the n, 20 plus 4 arctan n over 6 to the n. Once again, we have an alternating piece. So there we go. Now, first thing that should jump out to us is we've got this weird arctan of n in there. Arctan of n is a bounded function. So arctan n, bounded function. What we know about arctan of n is that it always lives between negative pi over 2 and pi over 2. What do bounded functions often use? Well, the sort of presence of a bounded function tells us we might want to try direct comparison test. Now, comparison tests require that you have always positive terms. We do not, so we'll need to put this in absolute value first. So we're going to consider the absolute value, a sub n. So that means we're looking at 20 plus 4 arctan n over 6 to the n. The idea is that this numerator, since arctan is bounded, 20 plus 4 times arctan, should be similar to a number over 6 to the n. Now, this might not look great, but if you just think about putting that number outside, that would be like a number times the sum 1 over 6 to the n, which would be like a number times the sum 1 over 6 to the n. And what is this? Well, this is geometric. This is a geometric series. R equals 1, 6, which in absolute value is less than 1. So this converges. So our expectation is that this thing should be similar to a convergent geometric series. But to do that, we're not going to use LCT, but because of this bounded function, we're going to use DCT. So what does that mean we need to do? Well, we need to show, since we're going to be comparing it to something that converges, we need to show that this is smaller than something of this form. So we need to show that 20 plus 4 arctan of n over 6 to the n is less than or equal to some number divided by 6 to the n. If we can do that, then it doesn't matter what that number is. That number divided by 6 to the n is guaranteed to be a convergent series. Our terms will be smaller, so our series will converge. How do we figure out the appropriate number here? Well, we can use these bounds. So as a little scratch work, just to make this a little bit easier, keep in mind negative pi over 2 is less than arctan of n is less than pi over 2. That means 4 arctan of n is somewhere between negative 2 pi and 2 pi. And if we add 20 to all those, we'd say that 20 minus 2 pi is less than 4 arctan of n plus 20 is less than 2 pi plus 20. So 4 arctan of n plus 20 lives somewhere between 20 minus 2 pi and 2 pi plus 20. Since we want to make sure that this is less than this, the bound we'd want to choose is this right here, 2 pi plus 20. So what we would say is our proof here is 20 plus 4 arctan of n over 6 to the n is certainly less than or equal to 20 plus 2 pi over 6 to the n. Check. So that's a number over 6 to the n. I mean, 2 pi is like 6 point something, so this is just like 26 something. So certainly our terms are less than a number divided by 6 to the n. So by DCT, and since a number times the sum 1 over 6 to the n converges, so does sum 20 plus 4 arctan n over 6 to the n. Okay, so we now know this thing converges. Was this our series? Well, our series had that minus 1 to the n in it. We put it in absolute value, and it converged. So that tells us our series, sum minus 1 to the n, 20 plus 4 arctan n over 6 to the n, is absolutely convergent. That's what this tells us, because we put it in absolute value, and by DCT, it's still converged, so our series is absolutely convergent. So this is a typical example of where you would use DCT because of the fact that it was bounded. It was a bounded function. Sine, cosine, arctangent, all of those bounded functions, DCT can be useful on them. All right, only got a couple more to look at here. Let's go ahead and take a look at this guy. We've got the sum from n equals 1 to infinity, 4n squared plus 5, n squared plus 3, all to the 3n. Looks pretty complicated, but notice everything is to the 3n there. So we have a single term to f of n power, in this case 3n. That tells us this is a prime candidate for root test. Because what are you going to do in root test? You're going to take this whole thing and put it to the 1 over n, and that's going to cancel nicely with that there. So root test seems like a good choice here. Also keep in mind, this thing has always positive terms, so we can rule out conditional convergence here. Okay, let's look at this root test. Limit n goes to infinity, absolute value an to the 1 over n. That's going to be limit n goes to infinity, 4n squared plus 5 over n squared plus 3 to the 1 to the 3n, and then all of that to the 1 over n. This is always positive, so we can drop those absolute value bars, and we get the limit as n goes to infinity. Once we drop those absolute value bars, 3n times 1 over n, because power to a power you multiply, you get 4n squared plus 5 over n squared plus 3, all of that cubed. Okay, now, we could, if we really felt like doing a bunch of algebra, distribute this third power onto everything in here and FOIL it all out. But that's way messier than we need to. Instead, we can be a little clever here and figure out what's going on inside here. So let's go ahead and multiply top and bottom inside our expression like we normally would with 1 over n squared. And our cube is still out there. This is what we would normally do if there wasn't that cubed. So let's just try to analyze what's going on the inside. So in here, looks like we'd get 4 plus 5 over n squared and 1 plus 3 over n squared, all cubed. So what's going to happen in here? Well, this is going to be 4 plus 0. This is going to be 1 plus 0. So it looks like this should go to 4 over 1 cubed. So notice we are avoiding having to do all the messy sort of algebra of distributing that third exponent. Now, of course, 4 cubed, we know that that's just 64. That is, of course, greater than 1. So by root test, this diverges. Okay. This is a classic example of using root test, right? It's sort of the expression itself just calls out for root test because everything is to a 3n exponent, so that root test simplifies things very nicely. All right, let's move on to our next one. We've got this guy here. We've got the sum 5 to the n plus 3 to the 2n, 10 to the n minus 6n to the minus 1. This looks pretty messy here. You might say, well, everything seems to have n exponents. Let's take a root test and put it to the 1 over n. But keep in mind that's going to be very challenging to work with because unfortunately if we put this all to the 1 over n, that 1 over n doesn't distribute over the addition and subtraction. So we're going to be sort of stuck there. Instead, let's see if we can do a little bit of rewriting. Remember, we have this idea that if everything's the same sort of term, then we should really only care about the most important ones, or the most dominant ones. We've done that a lot with polynomials, but these are all exponentials, so we can use the same sort of logic. If we do a little rewriting, let's try to get everything in terms of an n exponent just so it's easier to compare. We should be able to sort of see this as 5 to the n, 3 to the 2n. Well, 3 to the 2n is the same as 3 squared to the n. So that's 9 to the n. Down here, we have 10 to the n. And I'm going to factor out a minus 6 to the minus 1 times 6 to the n. So now I can sort of see that my numerator has a 5 to the n and a 9 to the n, and my denominator has a 10 to the n and a 6 to the n. Obviously, the 6 to the minus 1, that's just a number. We're not going to pay too much attention to that. Okay, so what should be the most important? Well, if we think about it, in the long run, this should probably, the 9 to the n should matter up top, and the 10 to the n should matter in the denominator. But that, of course, is just a 9 over 10 to the n. And what do we know about that? Well, that converges as a geometric series, since r equals 9/10 is less than 1 in absolute value. So, what are we going to use to say that this acts the same as this? Well, notice what we're doing is we're just getting rid of the unimportant terms. So, even though these aren't polynomials, this should be an LCT. It also helps that everything here has always positive terms, so we're going to be safe with that. So, let's try that LCT. We're going to take our limit as n goes to infinity. The terms of our series, all divided by that 9 to the n over 10 to the n. Then we can flip this up, and remember when multiplying, the bases are going to multiply here. So we're going to get the limit as n goes to infinity. Looks like we should get 50 to the n plus 90 to the n. And then when we swing this up there, we're going to get 90 to the n minus, and then looks like 6 to the minus 1. And when we multiply that, that 9 up there, 54, excuse me, 54 to the n. Okay. This looks pretty horrendous, but remember we'll run into things like this back when we were dealing with like sequences. The trick here is to multiply by the largest base in the denominator, so 1 over 90 to the n. And we get this limit here. Looks like it would be like 5 over 9 to the n plus 1 over 1 minus 6 to the minus 1. 54 divided by 90, I guess that's like 6 divided by 10 or 3 divided by 5. Sure, yeah, 3 over 5 to the n. Okay. Why did we build these types of things? Well, remember, as n goes to infinity, if the base is less than 1, then these go to 0. So this is going to be 0 plus 1 over 1 minus 6 to the minus 1 times 0. But of course, that is just going to be 1. And that is finite and non-zero. Check. So the LCT worked. So this acts the same as this, and this converges. So we can say by LCT, and since sum 9 over 10 to the n converges, so does our series. So we know our series converges. What type of convergence? Well, this guy had only positive terms, so it must be absolutely convergent. So our series is absolutely convergent. So the only reason I wanted to do this one is that it's actually very similar to some of the other ones we used to LCT. It's just to remind you that LCT gets rid of the sort of non-necessary terms if they're all of the same type. In this case, everything was exponential, so we were just able to pretty much ignore the 5 to the n and the 6 to the n and just focus on the most dominant terms. LCT starts to break down when you have different types of things, like if you have polynomials and exponentials. That's where you then need to use something like a ratio or root test. But when everything is the same type of thing, you should be able to get away with an LCT. All right, I believe we have one final one for this sort of massive summary that we've been doing here. So for our last one here, we've got minus 1 to the n, e to the n squared over n factorial. We see a factorial in there. So we know immediately this should be a ratio test. All right, let's go ahead and look at this then. If we take the limit, absolute value, an plus 1 over an, well, that should be the limit as n goes to infinity. For an plus 1, we would have minus 1 to the n plus 1, e to the n plus 1 squared over n plus 1 factorial. Pretty complicated up there. And in the denominator, we'd have minus 1 to the n, e to the n squared over n factorial. Okay, let's go ahead and apply these absolute value bars to get rid of this stuff, and then also swing this up here, this down here. So we should get this as the limit as n goes to infinity. Looks like up top, we should get an n factorial and an e to the n plus 1 squared divided by, and in the denominator now we have n plus 1 factorial e to the n squared. Okay, this simplification we should be very comfortable with, right? N plus 1 factorial is the same as n plus 1 times n factorial, so we can cancel those. And we should get that this is the limit, n goes to infinity, e to the n plus 1 squared over n plus 1 times e to the n squared. Okay, now what about this? Well, we could simplify this a little bit. N plus 1 squared, we know how to do that. That's just FOIL. That's limit. N goes to infinity. E to the n squared plus 2n plus 1 over n plus 1 e to the n squared. Notice now you could cancel this with this. And you could get the limit as n goes to infinity. E to the 2n plus 1 over n plus 1. Okay, this unfortunately is still an indeterminate form. It's an infinity over infinity. And since we have an exponential and a polynomial, we would like to use L'Hopital. So to do that, we need to do a quick replacement theorem. So we have e to the 2x plus 1 over x plus 1. Then we can L'Hopital this and get the limit as x goes to infinity. 2e to the 2x plus 1, chain rule up top, and 1 in the denominator. All right, here we now know what happens there. That goes to positive infinity. What does that mean? Well, if we go back up, what were we using? We were doing ratio test. We got positive infinity. That is certainly greater than 1. So this implies by ratio test, our series diverges. So we know we have a divergent series by ratio test. Once again, the factorial here immediately told us that we're going to be using ratio test. Notice you might look at this and think back to what we did in the previous one and say, well, I thought the factorial was faster than an exponential. Well, if it had been e to the n, that would be absolutely true. The factorial should have won out and it should have converged. But now we have e to the n squared. And of course, e to the n squared, that exponent is growing at an n squared rate. So we've just found out that something like e to the n squared is even faster than a factorial. If it had been just e to the n, you can check this on your own. If this had been e to the n plus 1 and down here e to the n, then this thing would have actually converged. But that e to the n squared is incredibly fast, actually outpaces the factorial, causes this thing to diverge. This finishes up our summary of numerical series. If you guys want some additional practice, obviously you have your textbook exercises and your suggested exercises. There's also a document of just additional series practice posted in the file section of Canvas. You can take a look at that as well. For our next section, we'll be moving into 11.8, sticking with series, but instead of being a numerical series, we're going to be looking at series as functions. So we'll be sort of tying series together so far, which have been totally numerical, just adding up numbers, to functions. So we'll be looking at that through what's called a power series.